Next up we have Göran Appelquist, who's the Chief Technology Officer for Edgeware, and his pitch is on guaranteeing quality in IPTV systems. Göran currently serves as CTO in Edgeware. He brings extensive experience in project research at CERN, the European Organization for Nuclear Research, the High Energy Physics Centre outside Geneva in Switzerland, which he gained as a member of the Stockholm University research team. He previously held management and executive positions at Digital Visions, including Director of R&D, CTO, and VP with Digital Visions business unit. Göran has a PhD in physics from Stockholm University in Stockholm, Sweden. So, over to you, Göran. Thank you.
Thank you. It seems like we all get very weird introductions, but let's see what my physics background can bring here. First, it's good to notice that Swedish companies are in majority here today, so Edgeware is the second one. So let me just quickly introduce you to Edgeware. Edgeware has developed a complete solution for origination and delivery of video content that we sell to network and pay TV operators around the globe. So we currently have around 120 customers worldwide, and around 10 million subscribers are currently capable of getting their video service from Edgeware equipment. So what I'm going to talk about today is delivering premium TV services over IP. So I will start by just defining what I mean with IPTV and very briefly IP networks. We've had very detailed discussions about network architecture, so this will be at a completely different level. But anyway, and then look at some of the streaming technologies that we use for delivering a video in an IP environment, and especially the challenges of introducing the new streaming formats that are becoming more and more popular. That actually introduces some new things that you might need to think about if you want to maintain the quality levels that customers are used to from existing solutions. And then I will finish off with some quick notes on how to do this transition, what tools are available to help doing that. So first, what is IPTV? I mean, traditionally, TV services in a cable environment has been delivered over a QAM infrastructure. Today, most of these QAMs typically have a northbound IP interface to allow them to be placed at the edge of the core network, which is an IP network. So for us as a streaming server provider, this is also an IPTV system, since we deliver IP streams into a QAM that then reaches the cable customers at the end. This is a very well-known and well-established technology, and which has also been very successful in delivering high quality and also consistent quality TV services. So this will be the reference that I use to compare with when we look at the new technologies that are being introduced. Then in the cable environment, we also of course have the IP side with the DOCSIS path, which today is primarily used for high-speed data services. But now there is a lot of interest in moving the video services also onto this side, both for the existing video services, maybe to get more efficient delivery, or to completely get rid of the QAM infrastructure and have one homogeneous infrastructure for all types of services, video, data, and also actually video services coming in from outside. Another driver could be to introduce new type of video services to be able to reach new devices like smartphones and tablets that does not work equally well with the legacy type of video services. Then on this side, we also have the video services coming in over the top and hitting the same network. I will not spend too much time on that in this presentation, but they still exist in that framework. Then networks. So what is an IP network? And as I said, this will be very high level. We've seen extremely detailed network diagrams today. So But the question I wanted to ask here is, now if we go all IP, does it matter if this IP network is a cable network running over DOCSIS or if it's a telco network? And the conclusion I wanted to get to, and I think we can actually go straight to that, because is that in many cases it doesn't really matter. I mean, there will be bottlenecks in both types of environments. Now I'm talking about access networks here. So there will be bottlenecks where a group of users share some resource, typically bandwidth, and you may need to take that into account if you want to deliver a premium video service. And if it's over a cable or telco, in most cases, not all, but in most, doesn't really matter. So it's all going to be about IP and not so much about cable specifically. So what streaming technologies do we have here? I mean, we have the sort of legacy technology that has been in use for many years, where video is delivered using over IP, but using UDP as the transport protocol. We use that for broadcast channels, and then we can use Multicast as a way of efficiently deliver the same content to many users, which works fine both in the core and the access networks. For on-demand streaming, we still use UDP to push the video data to the clients, but then we add a separate control channel over RTSP to manage that on-demand session. This is well-known technology, works really well. Really no major issues with that, except for some new stuff that has come in that we will take a look at on the next slide. But over the last few years, a new streaming technology has got a lot of attraction, and that is HTTP-based adaptive streaming protocols. There are a number of flavors of these being used on the market, but they all share some common characteristics. First of all, we now have all content available in a number of different bit rates and possibly resolutions, typically called profiles. And each of these profiles are chopped up into small fragments, usually a few seconds long. And in parallel with that, we also have like a table of contents called a manifest or an index file that describes all these profiles that are available to the client. So a client now that wants to watch some video will start by downloading this table of contents to it, so it knows what variants are available. And then it will start requesting content from the server. And while doing that, it will also measure the available bandwidth. And then at each fragment boundary, it may take a decision based on the measured bandwidth to switch to another profile. So we have now moved decision making to the client. It's the client that decides what content and what bandwidth consumption will be used, in contrast to the RTSP side, where everything is pushed from the streaming server. Also, as a result of this, the bandwidth usage will vary over time, while in the RTSP or UDP case, it's constant bitrate, so we always know what bandwidth is being used. So if we compare these two formats, what makes them good and bad? And RTSP UDP, even though being a legacy format, it actually has quite a few advantages for delivering a premium video services. We should remember that the HTTP formats, they came out of the need for being able to deliver video over the internet, where you have completely different characteristics. But if you want to deliver a premium video service within an operator network, RTSP UDP still has some advantages. So first of all, it works both over a QAM infrastructure and an IP/DOCSIS infrastructure. So going all IP doesn't necessarily mean that you have to get rid of RTSP UDP as a streaming format. Being based on UDP means that it's natively supports Multicast, which is really efficient for delivering broadcast TV. And then we also have a huge installed base of set-top boxes that supports this format, and these may not support the new formats. That, of course, is going to change over time, but right now there is still a lot of clients out there that doesn't support anything but RTSP over UDP. Finally, something that is maybe easy to forget, but UDP is actually a very efficient way of delivering a a bandwidth efficient way of delivering video or any type of data over a network. If you want to deliver video with the same bitrate using TCP, you will need a lot more overhead in the network to get the same sustained performance due to the characteristics of the TCP protocol. With TCP, there is also a proximity effect. So the further away the client and the server is, the lower is the bandwidth that you can get due to the increase of round trip times in the network, which you don't have with UDP in the same way. So there are quite a few advantages with RTSP UDP still. So why would we be interested in introducing some new formats? Well, the main driver is, of course, that we want to reach or introduce new services to reach new devices. All of the new devices that we see on the market, like smartphones and tablets and so on, they support HTTP adaptive bitrate, and they normally don't support RTSP over UDP. There are no technical reasons for that. It's just a design decision. They have not been designed to do that. Of course they could, but they don't, at least not today. So if you want to reach these new devices, HTTP is the only option. The second driver, especially if we can start getting some of these legacy clients to support these formats, is of course the sort of holy grail of being able to have one format that can reach all devices. And based on the adaptiveness of these protocols, it means that they also work very well in heterogeneous network environments. So if we have these formats, it means that we can deliver the same service not just to clients sitting on our own network, but to clients sitting on other networks, like mobile clients or clients connected to a competitor's network. So it opens up a new, a number of new possibilities, and that is of course very attractive. So now we will look at some. So if we assume that this is, and I think everyone agrees on that we will start to see more and more of these HTTP-based streaming services. What does that mean if we want to reach the same quality levels as customers are used to from the existing solutions? There are actually some differences that we might have to consider. So first I will talk about sessions. Sessions is a very well-established concept in the RTSP world. It's something that we use to allocate resources. We use it to report usage of content so that we can see what content is popular and so on. It's a very neat concept to have. And it's a native concept in the world of RTSP. A session is well defined. It's defined by a start time and an end time and some content that we have watched. And when we know what content we have watched, we also know the bitrate, because the bitrate is constant and never changes, and it's being completely controlled by the server. On the HTTP side, it becomes more complex. First of all, what we typically refer to as a session in the RTSP case is now, in most cases, a number of parallel streams going between the server and the client. So there can be one stream for video data, another for audio, another one for subtitles. And in addition to that, the client can also read data at multiple positions in time on the same stream. So for example, a client that watches a live stream but has decided to time shift a little bit, so he's 5 minutes behind the live point. Such a client might read data both at the actual playback time, but also at the live time to see the new data that is coming in. So you might end up with a huge number of parallel streams going between the server and the client. And we have seen some of the latest HTTP clients are actually using 10 parallel TCP connections between the client and the server just to get one stream of data. So a session is now much more complex than it is up there. In addition to that, HTTP is by nature a stateless protocol. There are no sessions. There is no control between the client and the server to define a session. So we have to do something, and of course there are ways of doing that, and these have been well established since a long time. We can introduce some kind of virtual session concept on top of HTTP. This is standard web technology that is used all over the web, and that can be applied here as well, and it works decently well. I mean, you can use naming conventions or other mechanisms to define some kind of session that collects all of this stuff into one something that we can refer to. So now we have a session, and when a session starts, it's pretty easy to understand. That's when we get the first request from a client. And up there, a session ends by a specific command from the client. The client tells the server that now I'm stop watching and you should kill the session. But down here, when does the session end? There is no communication between the client and the server telling the server that the session ends. The only thing that we will see is that suddenly the client stops asking for data. But is that because he has paused, or is it because he has stopped watching? We don't know. The only thing we can do is to wait. And after enough time has gone and no more data has been requested, we can probably safely assume that this session has ended. So then we can end the session, and of course we can then backtrack the end time to the last request that we saw, so we get an accurate end time. So that's pretty good and matches fairly well with what we are used to. But if we use sessions as a way of allocating resources in an access network, for example, that is not so good, because it means that we have locked up resources throughout this timeout period that were not used. So that might not be super optimal. Another issue is bitrate. Up here, bitrate is well known. It's always CBR. So as soon as someone asks for some content, we know what bitrate this client will need throughout that session. That's easy. But down here, we're now giving control to the client. So the client controls the bitrate. So at the first request, we don't know anything. So what is the bitrate of an HTTP session? Well, for reporting reasons, it might be okay to use some average bitrate, for example. That might be good enough, or the maximum. But if we want to allocate resources using this concept, what bitrate should we allocate? We can decide to allocate the bitrate of the highest profile available for this content. That would for sure make the client happy, because he will get a good quality throughout the session. But it might be a waste of resources, because we don't know if the client will ever use that profile. He might be sitting on a poor Wi-Fi network in the home, so he will not be able to use that. So he will just use half of that, and then we have wasted resources. Then we can go for something in between, like the average of all profiles or the middle profile or whatever, and hope that if we have enough clients that share the same pool of bandwidth, they will all get decent quality. But we don't know for sure, but at least we can hope for that. So there are some issues around allocating resources in this world that you don't have with the legacy stuff. Final issue I wanted to bring up in this context is reporting. Again, that is very easy when you have an RTSP setup, because the session is easily described. It's the start time and end time and the name of the content. That's it. Then you know exactly what has happened throughout that session. Down here, a session is now a lot of different events, and a lot of stuff happens. Depending on what you want to use it for, it might be okay to report a session with start and stop and content name and maybe the average bitrate. That might be good for analyzing popularity of content, or how much money you have made on certain content and so on. Then that should be okay. But from an operational perspective, that might not be good enough, because a lot of stuff can have happened throughout this session that you don't see if you do it like that. So two customers with the same average bitrate might have got very different user experience when watching this video. So probably you need more information than that. But how much do we need? Do we need the full resolution that we have, which means that we have to log every individual request that we see from the client? For watching a full-length movie, that could be 10,000 events that happens throughout this session. Logging all of that would put an extreme load on any type of monitoring system, especially for a large-scale video service. So do we need all that data? Or maybe it would be good enough to aggregate locally this data into some sort of reasonable resolution. Maybe aggregate it and sample it once per minute or something like that, so we get down to a few hundred log entries per movie instead of 10,000. That's also something that you might want to consider when introducing these type of services. Then we have the question of quality in terms of delivery. I mean, HTTP by nature is a best effort protocol. So does that mean that we can just turn it on and leave it and hope for the best, and then all clients will get the best possible quality? Maybe, I think is the answer. I mean, if you have enough bandwidth, then yes, that would actually work. I mean, if you have enough bandwidth, a best effort protocol will give each client the best possible quality. And the success and that might not be as bad as it sounds, because in many cases there is a lot of bandwidth available. I mean, the success of services like Netflix is a good example of that. If there wasn't enough bandwidth available, they could never deliver that type of service. They deliver it over the top, basically. They don't even have a network. So apparently there is quite a lot of bandwidth in many cases to deliver at least a service that people are prepared to pay for. Whether it is as good as the traditional pay TV services is something that I don't really want to get into. But anyway, that is definitely an option. But if you want to, it means that you have to throw bandwidth at the problem. So you don't really use the resources in an optimal way. So if you want to do that, then you will need to introduce some sort of resource management. And then, of course, there are lots of options for doing that. And I will not touch all of them here, but just mention some examples of what could be done with different levels of management and also different levels of effectiveness in terms of resource usage. So the simpler thing that we could do is just to prioritize traffic, and that's probably something we want to do anyway. We want to make sure that, since now we're running over an IP pipe where we share that pipe with lots of other traffic, not just the video service. So we have data traffic, we have other external video services competing for bandwidth. So at least we want to prioritize our own video service. But that is a pretty lightweight and pretty coarse way of managing bandwidth. It will not allow you to do on a per stream or differentiate different streams. It will just tell you, or basically define the order of delivery of data to make sure that your data hits the client before other stuff that is not as critical. We also have the option of limiting the options for the client. We have now given sort of the control to the client, but it is based on the knowledge that the client has. So it can only make choices between the options that you give to the client. So even though you might have a 4K version of a movie, it doesn't necessarily make sense for an iPhone user to watch that 4K version. So when you see that it's a smartphone user that tries to ask for content, you can actually create a dedicated manifest for that specific user, and in that manifest you remove the 4K version. If it's an iPhone, you might even decide to remove the HD version, because that might not make sense either. So you can quite easily, and this is standard technology that is available today, you can quite easily create per client or per request manifest and limit the options available to the clients, and hopefully then for a group of users, again sharing some pool of bandwidth, that would give a better utilization of those resources and give all clients a decent quality. Then we can go all in and apply the model from the RTSP world and allocate bandwidth per session. But then we will hit the issues that we discussed on the previous slide. What bandwidth to allocate? Should we allocate the maximum bandwidth, or should we allocate something else? And for what group of users should we do this over, and so on. So it's not as trivial as it used to be, but it's definitely an option still to do, and probably the one that would give you the best possible quality of experience today. Finally, I wanted to throw in something that is a bit controversial and actually today at least just a theoretical idea. I don't know of any available solutions for this. But the idea here is to basically turn everything around. Now we said that adaptive bitrate is based on clients making all the decisions. But is that the best way to do it? All the clients, or each client is not aware of any other client, and they all try to get as much bandwidth as they can to maximize their own quality. So will that result in the best use of resources when you have pools that is shared by a number of users? I would like to argue that it's not, and it's actually better to turn it around and let someone sitting on the other side to do that. And since this is based on TCP delivery, it means that both the server and the client has exactly the same knowledge about the available bandwidth to each client. And then I would argue that sitting at a position where you see a group of clients that all shares this pool of bandwidth, and you know the bandwidth to each of those clients, then you can make better decisions on what content to deliver to each client than each of these clients can do by themselves, where they don't know anything about the rest of the world. But this is a bit controversial, and as I said, there are no, to my knowledge at least, no solutions for this today, because it somewhat contradicts the whole concept. And for this to work, it must of course work with existing clients. I mean, the whole drive for these new formats is driven by client availability. And still, I mean, most of the formats that we see are the vendor-specific formats, which is because those clients are most common on the market. And we also see that with MPEG-Dash, which has been, at least in my view, slower in adoption than everyone thought, because again, there are no abundance of clients available. All of the major clients support the vendor-specific formats. So for this to take off and be a viable solution, it must work with the available clients, either today's clients or at least with tomorrow's clients. But there are some indications that it's actually possible to do this, even with at least some of the existing clients on the market. Next topic is Multicast. And this is just a dumb introduction. So this is Multicast in the traditional sense, where we use it for delivering UDP streams. And then the benefits are, of course, obvious. I mean, instead of delivering individual streams to each user, the same stream to each individual user, we deliver one stream that is copied to all users, and the ones that want to watch that content can listen to that same stream. So for each user we add, we save more bandwidth. And then if we have a lot of channels, then we don't start to see bandwidth savings from the first user, but it takes a little time. But after a while, the benefits will increase, and then after a while saturate when we have enough users. And if we add channels, this curve will shift to the right, because we're now spreading the users over more channels, so there are fewer users per channel. But then we can introduce technologies like switch digital video and remove those channels that has very few or no viewers from the access network. And then we can push the curve to the left again. So this is standard multicast that we're all used to. Very efficient and works well. So what happens when we switch to HTTP? Does that mean that we can no longer use multicast? If so, that would mean that all broadcast or live channels needs to be delivered as unicast, which would result in a huge increase of bandwidth in the access network. So that would be pretty bad. Fortunately, it is still possible to use multicast even with HTTP streams, but it requires some special treatment for it to work. It's not natively supported, so you need to do some stuff to make that work. So first of all, in this case, a stream or a channel is no longer one content only, because two clients can be watching two different profiles, and they can switch over time. So at a specific point in time, even though they watch the same channel, they might not be watching the same data, basically. So in order for this to work, it means that we have to push all of the available profiles over multicast to all clients. Otherwise, because we don't know which one they will decide to watch at a specific point in time. In addition to that, the clients still expect to request fragments over unicast, pulling fragments from somewhere over unicast, and they make the decision, which is sort of contradictory when we're now pushing content over multicast. So somewhere we need to convert from this multicast feed into something that the client can work with. So we need to introduce some kind of local temporary storage or caching close to the clients. And this can be in the residential gateway, or potentially it could even be in the client, even though I don't think that really makes sense, because then you would have to push all the profiles all the time into every client, which sort of contradicts the whole idea of adaptive bitrate. But having it in a residential gateway might still make sense, because then you can share that functionality with all the clients that you have in the home. And it's a fairly lightweight module. Depending a little bit on what format you're using, you need different functionality in that box. I mean, over Multicast we're pushing continuous streams typically, so at least you would need to then segment those streams into these small fragments locally in that cache. And in some cases that's enough. I mean, some formats like Apple HLS and one of the MPEG- variants, there we actually use MPEG transport streams as the encapsulation format. So that would be enough. Just segmenting those continuous streams would be enough to deliver an AVR feed on the other side. With other formats, you might need to repackage the content and change the encapsulation format. So that is a bit more heavy to do, but could still be done. If you don't want to do that, the other option is to not deliver. Yeah, I should also mention for this first case, I mean, most of the AVR encoders on the market today, they can actually create multiple synchronized transport streams, one for each profile. So that maps really well into a standard multicast delivery infrastructure, so you can just plug it into there. So then the only change will be in that local cache. The other option is to use a multicast technology that allows you to deliver files over multicast. Then you can deliver the actual fragments instead of a continuous stream. And then the only thing you need in that local cache is some way or support for that multicast technology for delivering files. And the cache needs to be very small, since you only need to cache one or a few of the latest fragments that are delivered on that live channel. So it's a pretty simple device, but you still need to do something. Multicast doesn't work out of the box. So since now one channel is converted into multiple profiles, you don't get the same savings as you do with UDP-based or CBR multicast that we're used to. So this curve again will move slightly to the right when we switch to adaptive bitrate content, but you can still use multicast to get similar benefits also here. Finally, how do we get from where we are today into an all-IP environment? We've heard a lot of CCAP already, and there are a lot of benefits of CCAP that has to do with OPEX savings and CAPEX and higher densities and so on. But what I wanted to bring up here was another benefit that is relevant to this discussion, and that is that it allows you to go from a physically separated infrastructure where you have dedicated QAMs for broadcast channels and VOD streams and CMTSs for data and so on, into a more logically separated infrastructure where you have one or several universal edge QAMs that can support all services, and you can then allocate resources through configuration instead. So by having that type of infrastructure, you could then gradually migrate from the existing QAM infrastructure for video delivery onto a DOCSIS IP-based delivery infrastructure. And this decision on when to do this is not as critical any longer. You can let that be driven by demand for new services or rollout of new set-top boxes or alignment with other parts of the ecosystem that needs to be transitioned as well. So CCAP is one tool that could help you out with that transition. But if you do that, I mean, it means that, yeah, if we look at the next slide. If we look at resource management again, on the QAM side, this is standard stuff. We all know how to do this. You have a session resource manager managing your on-demand sessions, or an edge resource manager. That's pretty standard. But on the IP side, If we do it like that. On the IP side, there are lots of more options. So exactly what to do there is not as clear. And also you have a more complex setup because you're now mixing traffic from both the video service and the data services. So what to do with resource management on that side is not as clear. And if you go for a gradual transition from the QAM side to the IP side, it means that during a period of time, you will actually have both options available. So what you really would like to have then is some kind of hybrid resource manager that understands both sides and can make decisions per session on which side to use. So you can still continue to use both sides and do it in the most optimal way. And this type of device, I'm not aware of existing yet, but I'm pretty sure that we will start to see that pretty soon, because this is a situation that I think a lot of operators will end up in. So, final slide. We will get a number of new opportunities by going to an all-IP delivery infrastructure. We can more efficiently use our resources, we can reach new devices, introduce new services, and potentially, at least over time, it gives us the possibility to end up with one single format or one single infrastructure for delivering video services to all possible devices and over all possible networks. But it also comes with some new challenges. HTTP ABR is not the same as the old RTSP UDP stuff that we're used to. It introduces some new characteristics that you need to consider when launching these kind of services. Resource management is not as trivial either. It will be a trade-off between the amount of overhead that you can accept and how well managed or the type of quality levels that you want to maintain. And in general, I mean, adding more devices and more types of networks, of course, makes the whole thing more complex. But there are tools like CCAP available that will help you smooth this transition. And when you do that, I mean, now we've just talked very focusedly on the streaming protocols and so on. But of course, when you switch from one side to the other and go for all IP and introduce new formats, it's also important that the rest of your ecosystems can support such a mixed environment. Okay, that's it. Thank you.
Thank you very much, Göran.